This video is about power distribution at low voltage by stepping down medium voltage. The medium voltage to be stepped down depends on the one that is available at the location of the project or at the location of the building. The medium voltage could be 33 kV or 11 kV. In this video, the mains voltage is 11 kV, which is stepped down to 400 volts for low voltage distribution. Please do subscribe to my JK Multimedia Solutions channel, and do follow me in this video as I make use of an example to illustrate the concept. Thank you. Now, moving on with examples. A building is located where the available mains voltage is 11 kV at 50 Hz frequency. Given that the building phase loads are red phase 47 kVA, yellow phase 50 kVA, blue phase 45 kVA. A. Calculate the building total load. B. Determine full load generator size or rating for the building. Calculate the transformer rating for the building, that is C. D. Calculate the building full load, star phase and line currents. E. Compute the building transformer maximum delta as star phase and line current. Determine, that is F. Determine the size of the main panel, interlock MCCBs. G. Hence or otherwise, draw the power distribution schematic diagram for the building. Neglect transformer losses. Moving on. Solutions to the problems. We know that mains voltage is equal to 11 kV at 50 Hz frequency according to the question. And we have a red phase load as given, being equal to 47 kVA, yellow phase load 50 kVA, blue phase load 45 kVA. Now, the A part, building total load is equal to 3 times 50 kVA, that is 3 times the highest phase load. It will be incorrect to take the algebraic sum of the phase load. Alright, this is the right answer, 150 kVA. Alright, B, full load generator size is equal to 175 kVA. That is the appropriate generator size. And you can see that it's slightly greater than 150 kVA. So this is appropriate. Now, C part, add 10% to 150 kVA, and that will give us 165 kVA. Now, transformer size is equal to 200 kVA. That is the readily available transformer size in the market that is very close to 165 kVA. It has to be close and higher than 165 kVA. That is 200 kVA. And the voltage is 11 kV on the primary side and 400 volts on the secondary side. The primary side is delta, while the secondary side is star, and the frequency is 50 Hz. Moving on. Reading, the D part question is meant to be building actual load phase current on star. Alright, so we have this. This is the delta side, which is the primary side, and the secondary side being the star side. Now, phase voltage is equal to line voltage divided by √3, and that one gives us 231 volts. So now, actual load red phase current is equal to 47,000 VA divided by 231 volts, which is equal to 203 ampere. And similarly, actual load yellow phase current is 50,000 VA, okay, divided by 231 volts, which is equal to 216 ampere. And the actual load blue phase current is equal to 45,000 VA divided by 231 volts. So, and that will be equal to 195 ampere. For star connection, R line is equal to I phase. This is star connection, this is star here. So the phase current is always equal to the line current. So I line is equal to I phase. Therefore, actual load I line read is equal to 203 ampere, just as it was calculated here. And the actual load I line yellow is equal to 216 ampere, as it is here. And actual load I line blue is equal to 195 ampere, which is the same as what was obtained here. Now, E part, note, apparent power in three-phase circuit is given by S is equal to root 3 V line I line, which is also equal to 3 times V phase I phase for both delta and star connections. Now, let's look at the E part. Building transformer maximum phase and line current. This is the primary side connected in delta and the secondary side in star. This is the transformer itself. So for secondary side, we start with that one, which is connected in star. The transformer rating is 200 kVA, and that is the maximum power it can deliver or it can handle. So therefore, making use of this formula, so we have this is S, which is equal to 3 into V phase I phase, which is this, and from there we calculate I phase, or the phase current, to be 289 ampere triple phase with neutral. We have the three phases and then the neutral here. Alright. For star connection, I line is equal to I phase, which is equal to 289 ampere in this situation. And what we are saying here is that the line current there is the same as phase current. Now, for transformer primary side, which is connected in delta, I line is equal to the apparent power 200,000 VA divided by root 3 times 11,000 volts, giving us 10 ampere triple phase. So we have red, yellow, blue, triple phase without neutral here. So, and then from there, we calculate I phase to be I line divided by root 3, which is equal to 6 ampere triple phase. Now, moving on. F part, size of the main panel interlock MCCBs. MCCB means model case circuit breaker. So, we take 150 kVA that we calculated earlier to be the apparent power, and we equate it to 3 times V phase I phase. So from there, we calculate I phase to be 216 ampere triple phase with neutral, and the readily available MCCB in the market that is higher than this and very close to this is 250 amp triple phase with neutral. We can make use of 4-pole type. Alright, so that is the size of the circuit breaker. Alright, and then G part, power distribution schematic diagram, is what we have here. Now, this is the power schematic or power distribution schematic diagram. We have three sections, which is the main section, the generator section, and the load panel section as well. So from here we have the available voltage supply is 11 kV. Alright, and the transformer we are having is to be connected in delta star. So we have 11 kV, 200 kVA, delta star 58 transformer as calculated earlier. And we have this is the metering unit here, 3-phase. The metering is done at low voltage, and we have the circuit breaker protecting the cable here as a 250 amp triple phase with neutral. Alright, and the energy supply people, they prefer to have the circuit breaker on the load side. Alright, that is what they like. Actually, the actual, the best locator to have been before the meter, but they prefer having it here. Alright, now we come to the generator side. We have calculated the size of the generator to be 175 kVA, 400 volt line to line. Alright, and then here we have this circuit breaker, which is also complementing the function of the circuit breaker that the generator has. Alright, and it's going to be ingress protection 65 code. Alright, now we come to this load panel, which is a low voltage panel. So the mechanical interlock which is serving as the changeover unit or changeover device or changeover switch. Each of the interlock MCCBs is of rating 250 ampere triple phase with neutral, because it has 4 poles each of them. So then we have these LV bus sections, which is the load bus section. From there we have MCCB1, MCCB2, MCCB3 feeding loads A, B, C respectively. Each of these load A, B, C could be load center, a load center. So we have 3 load centers there, and we have a spare outgoing here. The size of each of these MCCBs depends on the magnitude of the load connected to it, and that is it. Finally, please do subscribe to my JK Multimedia Solutions channel and expect more informative videos. Happy viewing and thanks for watching.